Alright, so in this video we're going to be talking about how to find the integral of even powers of cosine. And in order to do that, what we're going to do is we're going to start off with a very simple case. So let's say we have cosine to the power of 4. Now unfortunately, we cannot do the same trick that we would normally use with odd powers of cosine, which is breaking it down into cosine x times lower power of cosine. In this case it would be cosine to the power 3. And the reason for that is that there's no simple expression for this in terms of lower powers of cosine or sine. So in this case, we cannot really do this kind of thing. It's not really going to be helpful. What we can do is we can take advantage of the fact that we know what the trigonometric identity cosine square x is. So this is equal to half plus half of cosine 2x. And now what we're going to do is we're going to express this integral in terms of cosine square x times cosine square x. Alright, so now what we can do is, well, we can just substitute that into each of these, and then we're just going to multiply them together. So we notice that we can factor out the half, and because we have half here and half there, those two get multiplied, so we get 1 over 4. We can carry that outside of the integral. So here we're left with 1 plus cosine of 2x to the power of 2 dx. So now it just becomes a matter of expanding this out. So in this case we can do that because it's a very low power. So we're going to get the following. We're going to get 1 plus 2 cosine of 2x plus cosine squared of 2x. Now obviously we can integrate this, we can integrate that, but we don't know how to integrate this, but we can use the formula again. So we're going to get the following. So we're going to have 1 plus 2 cosine of 2x. Now we use the formula, so this becomes half plus half of cosine. Now remember, this is 2 times the argument of x. In this case, the argument is going to be 2x. So we have 2 times 2x, which is 4x dx. Alright, now we have 4 terms, so we can perform the integration in the regular manner. Now this and that, you notice that you can add them up, so that becomes 3 on 2. So we're going to get 1 over 4 times 3 over 2x. This becomes sine, so we have sine 2x because we divide by 2, so that cancels out with that one. Now this we already added it to it, so we don't need it. And now we're going to have plus 1 over 8 of sine 4x dx. And now we could pretty much just carry out the multiplication. Actually the dx shouldn't be there, I already integrated. So plus some constant c. And if we wanted to make this a little bit more explicit, we could say, okay, let's multiply this through. So this becomes 3 over 8x plus 1 over 4 sine 2x plus 1 over 8 times 4, that's 32, sine of 4x plus some constant c. So this is going to be our final integral. And you notice that the only reason we managed to do this is because we reduced everything to a power of 1 on cosine. So when integrating odd powers of cosine, well, in this case even powers, it's not that more difficult than odd powers, because with odd powers what we would do is we would try to represent it in this form, but then we would have to expand out whatever we have here. But in essence it becomes easier because you can substitute this by something like u plus u squared. And then this is much easier to expand than having something like this, because when you expand that, you're going to have terms that are going to also have to be reduced. So in general, this is a little bit more tedious than doing the odd power integration. But you can get an idea of how this works. So if we were to say generalize this to say cosine to the power of some even number nx dx, then what you could do is you could break this down. So you would have the following. You would have cosine of squared x, and now you would have n to the power of 2. Now you know that n is an even number, so if you divide it by 2, it's still an even number. And now, actually, it's not necessarily an even number, but it is still going to be an integer. And you're going to have dx. And now what you can do with this is, well, you know that you're going to have a half in here, so this is going to become half plus half of cosine 2x to the power of n on 2 times dx. And now what you could do is you could factor out the 1 over 2, and then you could just raise that to the power of n on 2. So this becomes 1 over 2 to the power of n over 2 times the integral of 1 plus cosine of 2x to the power of n on 2 times dx. And now what you would simply do is, well, you divide. So if your power is, for example, 6, then this would be 6 on 2, that's 3. So you would perform this cubic expansion. It would be a little bit longer, but it would still have the same kind of outcome as this one. So you would just need to expand that out and then reduce everything to just a power of 1 that you can integrate using the regular formulas. But this is the general idea behind it. Now the same thing applies to sine. So let's say we wanted to do the same for sine to some even power n of x. Now we can break it down. We can say, okay, let half this equal to sine square x to the power of n on 2, because n on 2 times 2, that's becomes n. And now there's another trigonometric substitution for this one, so that one becomes half minus half of cosine 2x. So it still involves cosine, but you have that negative number there. So that's going to make things a little bit different. But nevertheless, we're still going to get a similar formula to that. So this is going to be 1 over 2 to the power of n over 2. Now you're going to have integral of 1 minus cosine of 2x. So you notice that this is pretty much the same formula. The only thing that is different is that now you have a minus here instead of a plus. So you can imagine that the terms you get are going to be alternating in sign, whereas these ones are not going to be. They're just going to be positive all the way throughout. And yeah, that's pretty much what you would have for even powers of cosine and sine functions. So now it just becomes a matter of how well do you want to define this. You could use things like the binomial formula to expand it out. You could use Pascal's triangle. But in general, you wouldn't really get very high powers of these functions. In practical situations, I don't think you would ever get something higher than power of 4 or 5. So as long as you know how to do these low power ones, I think you should be fine as far as applications go, I would say.